In this lesson, we'll consider another algorithm that's concerned with the topic of searching. And in this context, we'll look at a concept of analysis of algorithms and the complexity of algorithms. So often as computer scientists, we have to study the performance of the algorithm in various ways. So one of the ways that we're interested in an algorithm's ability to perform is in its time complexity. So is the algorithm fast enough? How do we compare one algorithm against another in terms of one being better efficient under certain circumstances? And the second criteria that we often want to look at is space complexity. So as the algorithm is computing its result, how much space does the algorithm need in terms of internal memory or disk space as it's computing its core result? So these questions about performance along the issues of time and space are often considered in terms of the input to the algorithm, that is, the size of the input. So if I have, for example, n elements in a list, that's this, I have to process n different things, and what's the speed of the algorithm or the memory requirements of the algorithm as it relates to the size, input size increasing. So in order to analyze the complexity of algorithms, we often talk about what's been called big O notation. So just to generalize this for the level of CS principles, you can take an entire course on this one slide. The idea of big O notation here is to discuss the worst case scenario for a certain input size applied to a specific algorithm. So we like to understand, for example, in performance, what's the rate at which performance decreases as the size of the input list, for example, would go up. So some examples, a linear time algorithm is an algorithm where the performance degrades at a linear rate. And what I mean by that is if I have n different number of items in a list, then the performance would continue to grow at a linear rate. So you could document the performance speed based upon the number of input elements in a linear straight fashion if you were to draw this as a graph. If I have a polynomial time algorithm or a quadratic algorithm here, the performance degrades. For example, if I have an n squared algorithm, the performance degrades to the square of the input size. So as the size gets larger, the performance starts to get a little worse. And then there's exponential algorithms and algorithms that as the size becomes much larger, the ability for the algorithm to process within a regional space or time becomes even more difficult. And there's all the other issues in computer science dealing with concepts of decidability and other kinds of theoretical things that we're not going to discuss here. And there's some exclusion statements also in CS principles so that your students don't need to know about these explicitly, but having a general notion of complexity and how we measure algorithms is essential. And it is actually a learning objective in CS principles, but not at a deep level. So you can see on this slide at the bottom the growth rates of the input size. So as the input is continuing, the performance of the algorithm increases or decreases. Having a logarithmic algorithm is actually a desired thing. So an algorithm that's log n the performance actually improves as the input size becomes larger. So we'll study the performance of algorithms in the context of searching. So searching is another great algorithm to consider. I mean, at its most basic level, abstractly, you could say that searching is the heart of Google. I mean, everybody's doing a Google search. There's been some other great lessons that we'll refer to in the lesson objectives that talk about search. And so this is something that your students can easily understand as well. So the idea is that given a set of input values, for example, a list of numbers, in search what we need to do is determine whether or not a specific value is included in that list. And a variation of that is to not only determine if the input value is in the list, but also to discover and find where that value appears in the list. So this was even a variation that we studied back in Unit 3 when we were discussing the concept of search and the built-in blocks for lists and how we then found the index for where the, say, smallest or largest value might be. So in order to discuss searching, I would suggest that you go and do things on the board or do unplugged types of events. So you can do linear search on the board where I would suggest you describe, for example, draw a list out onto the board and then role play the idea of searching through that list for a specific element. So in a linear search, there's no assumption about the sorting order. So a linear search, the values could be sorted or unsorted, and we can still find the desired element we're looking for. In a binary search, there's requirements. The thing or the list that we're searching through actually needs to be sorted. So there's some CS Unplugged activities that we can do with binary search as well. We hope to have references in the lesson plan that will give you some more information about that. And then there's also the example with the phone directory for binary search that's popular with students, where we rip up a phone book in order to try to find the location of a certain name. So in linear search, the idea is to, again, examine each component in the list. So we start at the very beginning of the list and work through every element until we reach the end. And what we're trying to find in a linear search is whether or not a specific element is in that list. So we compare the desired search element to every item in the list. If we find it, we either return true or we return the location where that appeared. And if we reach the end of the list and we haven't found the thing we're looking for, then obviously the thing we're looking for is not in that list. So the way we process a list for searching linearly is much like a checkout line at a store. So there's a line of customers in that list, and the checkout clerk will process each customer's purchase one at a time. So we're walking through a list, and each time the processing is comparing each element of the list to the desired thing that we're looking for. So you can try this out as an in-class example on the board, or ask for volunteers, and just maybe place 10 numbers on the board in a certain order, and ask the class to give you a number either in or out of the list, and role play what happens when we're searching through in a linear search. So here's an algorithm in pseudocode that suggests the concept of a linear search. So we're keeping track of the index in this case, the largest index. So largest index is the initial element, and also we begin from the very beginning of the list. And the repeat loop there is just iterating through every element of the list, and the subscript there of the L with the brackets and index and L bracket largest index, that's just a way to access a particular element of the list at the index or largest index. So if the element stored in the list at point or location index is greater than the element stored at largest index, then we found the new largest index. So we update accordingly this variable that keeps track of largest index. Then within that loop, we're going through every item, so we need to increment index by 1. And at the very end, we're printing, or we can say in Snap, what that value of largest index might be. Here is the implementation of a linear search in Snap. So we already have observed some of this in Unit 3, and we discussed this topic, but this is just revisiting this concept of finding the highest score in a list.